Well, hello and welcome back to Engineering 202. Welcome back to the laboratory, and we're going to tackle experiment number 5. Here's our handout, our procedure handout, and I know it's a little bit hard to see on camera, but you'll be getting a hard copy of this. Basically, it goes through setting up the circuit, some of the observations that we'll want to make. So I won't go into too much more detail in a moment. We'll go into one in a lot more detail as we talk about how this thing is hooked up. The other thing, and you'll get a hard copy of this also, are the questions, and likewise, I'm not going to go through those right now. We'll wait till we've kind of got the data under control, and then we'll talk a little bit about those. So with that, let's talk about hooking this thing up. I need to move the camera a little bit on you here. I'm not using the function generator over here. I'm using the built-in. This is just a transformer that's built in, a lot like the transformer you might have if you have a doorbell at your house, or the low voltage side of your furnace, running the thermostat wires and whatnot. What I've done is I've just tapped half of that transformer. And I'm going to take that as my input. That gives me a nice consistent source. I'll quit moving that camera for you so I don't make people sick, and that's what I will be using for this. The only the advantage to it is I get a nice constant source. The disadvantage to it is that I can't control the amplitude very well. Normally, if I don't know what the transformer is, I'm probably going to want to start out with a very low voltage. So if this were a large step up, that I wouldn't get too high a voltage on the output. Since I kind of know what this is, I'm going to go ahead and take the risk of starting with a little bit higher voltage on the input, and I think we'll be okay on the output. But if we really didn't know what this transformer was, this might not be a satisfactory source. But since I'm a little frustrated with the function generator here, I think this will work well today. So then we've got our circuit. Let's talk a little more in detail about how that's hooked up. We take the transformer and hook the black and blue wires together. So there's the black wire and there's the blue wire, and those are a little bit hard to see in real life, let alone on the camera, but I've hooked those together with a jumper wire, and we're referencing that with our ground connections on the probes. Then we apply a 60 hertz, this is 60 hertz signal across the 60 hertz sine signal across the black and the green leads. So there's the black and the green leads. So that's what I am inputting to. I've got this 100 ohm resistor here just for a little extra protection. Also makes it a little easier to hook the probe on there. So this is the input side. This is channel 1 measuring the input. This will be the output side between this red and this blue. And I've got the blue channel, channel 2, measuring that. This resistor here is just in here for the convenience of hooking the probe to it. It's not going anywhere right now. Eventually we'll hook it up when we get to the next part of this, but since it's just terminated and I'm measuring on this side of it, it's not going to affect my measurement at all. So this thing's been running for a while. It should be up to a stable temperature and whatnot. And I think we've got a pretty good display here. We've got channel 1, which is the input. That's the larger yellow one here. That's 5 volts per division. And channel 2, that's the smaller one. That's the output. And it is also 5 volts per division. Okay, these were close enough together, I decided just to put them on the same scale, so these are both 5 volts per division. This is also 60 hertz, so it's 2 milliseconds for division horizontally. I don't know that you know that number, but just to read that into the record, I'll do that. So with this picture right here, I mean, if you pause this thing and spend some time on this picture, you should be able to talk about the coupling of this thing. Is it a step up? Is it a step down? Where are the dots? Okay, if you're struggling with putting those dots in there and how do you assign that, go back to the end of lecture number 16, and that should help you with that. Now, you can use the scale here in 5 volts per division. Each centimeter, each division there is 5 volts on both of these. They're using the same scale. I'll also provide you some measurements. I can just take my digital voltmeter here. I've got that on AC, and we'll go across here. Make sure you can see that, yeah. So that's 6.78 on the input there. And then on the output, we have 2.22. Okay, and I think that correlates to the trend that you see on the screen, although if you multiply by this scale factor here, you see that those numbers don't match at all. But remember that on the screen, we're measuring the maximum amplitude. If you're going from here at the 0 point up to here, you're measuring the maximum amplitude, or likewise from there to there, you're measuring the amplitude. Whereas here, we're measuring the RMS value on our meter. So what we got from the meter was the RMS. If you compare RMS to RMS, you should be okay. If you compare the screen to the screen, you should be okay. You have to be careful as you try and go from the screen to the meter. With this sine wave or cosine wave, you're going to have that factor of square root of 2. And you got some practice with that in the three-phase lab last week also. So the maybe we'll look at the questions here. Draw the circuit for step number 1 showing the dot. So you should from this screen be able to get where the dots are. What's the no load coupling? We don't have a load on this, so we should be able to see the coupling. Does it step up? Does it step down? How much does it step down by? Is it a 1 to 30 or 1 to 40 to 1 or whatever that ratio is? Okay, so answer those questions. And then we're going to have to put the load on there. So we'll go back to this, number 3. Now put a 10 kilo potentiometer in series with a 100 ohm resistor. And the reason I do that is because when this goes to a 0 value, I want to still have some protection in there. I don't want to have a dead short. At one end of the potentiometer, it could be 10,000 ohms. At the other end, it could be 0 ohms. So I still want to make sure that I have a few ohms of resistance there. I mean, you could have said, don't turn the potentiometer to the extreme one side or the other, but that's sometimes hard to get students to do. So we just put a resistor in there. So let's see how that hookup goes. You can see I've come out of here. I've got this 100 ohm resistor. I'll put a wire in here that goes to this 10K potentiometer, and I could use a potentiometer like this one. In fact, I think this is what I was going to use. Yeah, it's 5K. The experiment was originally written for 5K, and this would be just fine. But I kind of like these built-in ones because they don't flop around and whatnot. So we'll go ahead and use the 10K one. And I'm going to use, this will get me hooked up here. So I'm now loading, coming through this 100 ohm resistor, through this potentiometer from one of the outside leads. There's the one outside lead. There's the other outside lead. So from the outside here to the middle and back to there. So that's what I've got going. So now when I twist this knob, you can see here that if I twist this, and you see the little this little indication on the knob, so hopefully you can see that the when the knob turns, as I turn this, I can turn it a lot and not have anything on the screen change. Okay, I move it around and you don't see that blue changing at all. But as I get down here to fairly low resistance, it starts to pull down. I'm getting a very low resistance. Very low resistance means very high load. Okay, very low resistance means a lot of current, high load, and it tends not to like that. But on the flip side of this, from about here on up, for higher values of resistance, it doesn't change at all. So we might think that over reasonable ranges of load, this thing maintains its properties. It maintains its ratios. So let's see. Let's look at the question. Does the coupling remain constant in this circuit with all values of the load? Well, I think that's one that you can honestly answer yes and no. There's some values that it stays very constant. These higher resistance ranges stays very constant, but when you really load that thing up, it doesn't. Okay, you're kind of being unfair with it down there. That's why we don't want to leave it there very long at all. We'll tend to burn it up if we don't burn up our source. And then the last thing that we want to do is we'll kind of move away from this. Maybe I'll even turn this off so I don't end up shorting some stuff out here. And it says, using the circuit provided by the instructor, try to quantify power loss due to transformers in the U.S. in most U.S. households. Okay, so that seems confusing, but I think we'll be able to demonstrate that a little better. Let me set this up here. So, a little different part of the experiment. Yeah, this should be okay. So, look at. Okay, this screen I know is a little bit hard to see, but I just have essentially an extension cord that's plugged into the wall, so hopefully I don't electrocute myself on camera. And it's a little kilowatt meter. This is just a cheap little meter. You can get them at places like Harbor Freight, and you can use it to measure the voltage and the current and the wattage and things like that. It's really kind of fun. Go around your house, you know, and measure things like that. So what I've got with this is I'm going to take some of these transformers that we have. Here's these are the little bricks. Maybe this one is a little more familiar to you. You got something like this. It's got a cord on it. You plug this into maybe a cordless phone or a toy or something like that. And this goes from 120 volts AC. You plug it in. And this one actually is 9 volts DC out. It's Radio Shack. So it got to be good, huh? So now, I don't have the appliance. I have a bad habit of saving these things after the appliance is shot and thrown away and whatnot. So this is not plugged in at all. It's not being used. I'll just leave that right there, and I'll go ahead and plug that into this. And what do we have? We got about 1.3 watts, 1.4 watts, teetering between 1.3 and 1.4. And I'm just going to take this on face value. This is not a high quality instrument, but we probably know that this is using some power right now, even though it's not running an appliance or a toy or whatever that might be. Okay, so there's some inefficiencies in here because it's drawing power, but it's not doing anything. You might say, well, that's because it's making DC on, so let's try another one. Remember that is 1.3. Set this aside. So this guy here, this little brick, it just doesn't have the cord on it. There's something you could plug into right there. Try to show that on the camera a little bit. So this is input 120 volts AC right there. Interesting, they've rated that in volt amps, so we should all know all about that. And this is 24 volts AC out. Okay, so this would be a great one to run a doorbell with. They're usually about 24, 26 volts, something like that. So this is not converting the AC to DC. This is converting it to AC. So this is AC to AC. So let's plug that in. And that's 2 watts. Okay, so that's 2 watts. So again, I don't have it hooked up to anything, and it's got 2 watts of power there. So it's got some inefficiencies, and it's AC also. And I wouldn't try and make any trends between the AC and the DC as being more or less. These are just different sizes. Let's try a little more modern ones. This one is one that you might put your cell phone in. It goes from AC to a couple of USB, so a USB charger. And we put that in there. We actually see it as 0. So this is a little more sophisticated. It's got some switching in here. It's really going to do some things at high frequency. You could do some research on the internet with this, but this is a lot more efficient, a lot more sophisticated, and possibly not more durable. These are pretty dumb. They're pretty durable, but there's a cost to that. And one of the things, you don't have to be a real electrical expert to tell them the difference between these is the physical weight. This has a good sized transformer in it. It's got some heft. You wouldn't want to throw this at someone. This one is quite a bit lighter. Okay, it's not only physically smaller, but it's quite a bit lighter. So you can kind of tell that. So in these older ones, and you know, even though they're older, probably got lots of those around the house. I mean, if you start to walk from room to room, you can probably find a few of these, and they may be in use, they may not be in use. But let's do some rough calculations with this. It'd be kind of interesting. I think I'll set this aside here. So the last question that we're going to look at here is, Said from, there we go, the meter's beeping. Says from the comments in step number 4, that's where we just made our measurements with the little kilowatt meter. Make an estimate of the energy lost per day in kilowatt hours if one considers all of the plugged in but unused appliance transformers in U.S. households. Okay, so kilowatt hours, if you use 1,000 watts for 1 hour, that's a kilowatt hour. So, so we have power, that is watts. We have kilowatt hours, that's a measure of energy. Okay. So assume each U.S. household has 3 of these little things, and they're dissipating 1.5 watts each. Okay, and that's roughly what we measured here. You could argue about whatever number you want. I just grabbed a couple that I had, so let's just go ahead and take 1.5 watts each. Well, they're plugged in but unused 90% of the time, okay, for a 24-hour day. So that gives you some numbers there. Also, how many typical households could be powered with this daily U.S. loss? Okay, and it says you will probably need to do some research to find approximations for some of the unknown quantities. I would assume that you're going to have to look up how many households are in the U.S., okay? And I wouldn't say houses, but households. And then also probably want to try and find the average power, or the average energy needed, I should say energy rather, for a typical household. And those are probably a couple numbers that you'll need to look at, and you'll probably get pretty decent numbers on those. I did some quick searches and came up with some pretty good numbers there. I think you'll be amazed how much power is being lost. And someone that maybe has one of these and has an older appliance on it or something, these numbers might not be that bad. I mean, we just measured around 1 to 2 watts, so 1.5, that's good. You got something, when you really think about it, you may not use it that much, so 99% of the time it may sit there being unused. So it's really kind of interesting when you start to total these things up, and you can see the reason for going to something like this. Probably in the end, one of the reasons they went to something like this is it's cheaper to make. Okay, this has a lot of copper in it, weight and things like that, but these are also probably quite a bit more efficient too. Well, with that, that gives you some work to do, and like I said, I'll send these to you in PDF form. And you can go ahead and get going with Lab 5 as we start to look towards the end of the lab. We've got to do finish up with Lab 6 next week, and we'll go from there. So until next time, take care, and thank you for watching.